Which one? It's a bird. It's moving across a plane. That one? No, we've had that one for a couple of years now. It's parametric equations. Okay. So that's how we're gonna start today, Carlos. All right. Okay. All right. All right. Now I know going in. Happy No Housework Day. Okay. I had two choices today. It was No Housework Day or Beer Day. I went with No Housework Day because we're in school. Honest to God. I really don't. I really don't. Yeah. That's good because you're not a date. Yeah. All right. So before break, for those of us that were here that Friday, in cold and snowy, the upper Midwest, we talked about parametric equations. Okay. So today I want to go a little deeper into what a parametric equation is. We have updated the backboard, so that is current for us. A couple of things to point out. So we're going to start with parametric equations today. We will get into graphing them, but today we're going to graph them by hand. You don't need a graphing calculator today. Tomorrow we'll graph them on a graphing calculator, and we'll start some circular motion problems. Okay? Then we'll do that Thursday also. Friday we're going to start launching an object at an angle, and we'll do that for a couple of days. Then we'll do some algebraic solving with no calculators. Then we're going to take an extended formative. So on the 21st of April, that's going to be an extended formative. Don't be shocked if there's a staple in that one. Okay? All right? And then on the 22nd, on Wednesday the 22nd, that is going to be day one of the launcher lab. And we have deemed that day to be a no conflict day. So if you have a conflict on Wednesdays, let your Wednesday teacher know that you will need to be in our class the entire time. Okay? Then we'll deal with launcher labs on Thursday. Friday we will start reviewing. Tuesday coming back, then we'll continue our review. And then on the 29th of April, which is the next Wednesday, so that you're in your same groups, you will be launching your projectile. Okay? Okay? And then that will be followed by the test the next day. Okay? Okay? For 2 straight Wednesdays, yes. Not the entire week, just those Wednesdays. Okay? And we deemed yesterday too that on those 2 Wednesdays, we're going to have seating charts on those 2 Wednesdays. Me and Schmeling are picking our groups that day. So, yep. Good times. Good times. No, that we plotted yesterday during our team plotting times. Yeah. Schmeling was a go-getter, and he's already got his done. So, yeah. I wasn't that big of a go-getter because I was getting the notes ready for today. So. All right. So, you have been dealing with functions. Where'd my good marker go? This is the bad one. Oh, well, I guess I'll just use it. Oh, well. You've been dealing with functions, and it's been like y equals f of x. Okay? You've dealt with that numerous times. It's been many times. I mean, you've seen it 1,000 times now. Something like y equals 4x plus 3. That's a linear function. Something like f of x equals 3x squared minus 7x plus 4. Okay, those are functions in 2 variables, x and y. Okay? Cartesian functions, if you will. In those functions, the x value, found it was just buried. The x value is your independent variable. what you plug into the function or the input. Okay. X is what you plug into the function. It's your input. Okay. Y then, or f of x, is your dependent variable. It's what you get out. It's your output. Okay? The value of the function, if you will. Okay? And then you can plot points, and those points then would be x, comma, y on a Cartesian coordinate system. Y is your vertical axis, x is your horizontal axis. Plot them all, connect them, blah, blah, blah. You've done it thousands of times in order to get to this point in time in your life. Okay? Today, we're going to start a parametric equation where now this is going to be a function. Actually, it's going to be two functions within a function, and we're going to have three variables. So now instead of it being f of x, now it's going to be f of t and g of t. Okay? Actually, this one should have been, one of these should have been g. We'll make the y one be the g. Actually, here, let me do this. I can do this. I know what I'm doing, even though it doesn't look like it. X is the one that was the G? Okay, that's fine. I can do that. He was distracted yesterday by smelling, picking his seeding chart. Okay, so you got two different functions there. T now is going to be time. And it is your independent variable. So it is now your input. Okay? Which means then that both x, which is a function g of t, and y, which is a function f of t, both of those are your dependent variables, or your outputs. So you have to take your t value and you have to plug it into the function for x to get the x part of the point that you're going to plot. Then you have to take that same t value and plug it into the y function and get out that number, and that's going to be the y part then. So the point that you plot is actually g of t, comma, f of t. And that point then is what you're going to put onto your graph. Now, I will tell you that your t values also come with restrictions. Meaning there's going to be a limit to your t's. Okay? T is not going to go on forever and ever and ever and ever. And most of the time, your parametric graphs are just portions of an actual graph that you would have normally seen. So there are no arrowheads on the ends of parametric graphs because they stop. Okay? Right? For those of you that were here Friday before break, we talked about Sal Frelick hitting a home run the day before. Okay? That ball doesn't continue on forever and ever and ever and ever. The flight of that ball doesn't continue on. Something will stop it. Either time, or a wall, or the ground, or somebody else's glove, or things of that nature. Okay? That ball does not continue on forever and ever. Okay? So let's get into graphing. We want to sketch this one by hand. So we're going without calculators here now. Okay? So this was how that restriction here looks. Okay? So we are only plugging in t values that are between -3 and +2. So that is what we put here in our expanded t chart. So we're starting with -3, then let's go to -2, -1, 0, 1, and 2. We're plugging just those values in. Okay? If I plug them into the x function, -3 plus 1 is -2. -2 plus 1 is -1. -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. But plug these green t values into this blue equation for t and got out my x values. Now I'm going to take these green t values and I'm going to plug them into my red function, t squared. -3 squared is 9. -2 squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. So now this point right here that I'm going to plot is the point -2, 9. And that's the point that I plot on my graph. -2, 9 is right there. This is the point -1, 4. That would be the next point that I plot. -1, 4. This is the point 0, 1. This is the point 1, 0. This is the point 2, 1. And this is the point 3, 4. Now, when I go to connect those, you're going to want to continue that parabola on, but that parabola stops at those points. You don't go any further than that. You don't put arrowheads on it. It stops at t equals -3, which would be the point -2, 9, and it ends at, or it starts at t equals -3, and it ends at t equals 2, which is the point 3, 4. Add. I don't like that thing. didn't do a very good job of coming back over. What, Kitty? We can make a parametric function into its corresponding Cartesian function by doing something called eliminating the parameter. And how we would go about eliminating the parameter is, the first thing that we would do is we would solve one of our functions for lowercase letters for t. Make it easy on yourself. Which function do you think is going to be easier to solve for t? X or y? X, okay? So let's solve x equals t plus 1 for t. What would you do? Subtract 1. So x minus 1 is equal to t. Yes? And then step number 2 is plug that into the other function. Okay? So my other function was y equals t squared. Scroll down here a little bit. Give myself a little more space. So it would be y equals t squared. Well, then that would become y equals, now instead of t, I'm going to put in x minus 1. Which, if you remember from your Algebra 2 days, is a parabola with a vertex at the point 1, 0, opening up and following the 1, 4, 9 pattern. So left and right 1, up 1. Left and right 2, up 4. Left and right 3, up 9. Well, if I follow that pattern, here would be my vertex right there. Left 1, up 1. Right 1, up 1. Left 2, up 4. Right 2, up 4. Left 3, up 9. Right 3, up 9. Which it would be if we were to graph it continuous, a continuous function, but we're just taking a little segment of that. Okay? Or if you wanted to expand this, we could also say here that this would be y equals x squared minus 2x plus 1. Parametric functions can also happen in the trigonometric world, okay, where we could have either our t values from either 0 to 360 degrees, or we could have said here from 0 to pi. Okay. Okay. So made it easy on ourselves. We plugged in the 45s there for you. So 4 cosine of t is my x value. Well, what is the cosine at 0? 1 times 4 is 4. At 90, what is the cosine value? 0 times 4, 0. At 180, what is the cosine value? Negative 1 times 4, negative 4. At 270, what is the cosine value? 0 times 4, still 0. At 360, what is the cosine value? 1 times 4, still 4. Okay. Now we just have the other ones. At 45 degrees, the cosine value is square root 2 over 2, correct? So if I'm doing 4 cosine of 45 degrees, that would be the square root of 2 over 2 times 4, which would be what? 2 root 2? Two square roots of 2 is the square root of 8, right? Right? Which is almost 3, correct? So we could say that that's approximately what? 2.8, 2.9? 2.83-ish? Did you actually calculate that in your calculator? And you got 2.83? Perfect. At 135 degrees, what is the value going to be? Negative 2.83. At 225 degrees, negative 2.83. And at 315, positive. Okay. Now let's switch over to the sine values. The sine at 0 degrees. 0 times 4, 0. 90, 4, 180, 0, 270, negative 4, 360, 0. Okay. For sine of 45 degrees is going to be 4 times square root of 2 over 2, which is going to be 2 square roots of 2 again, which is going to be approximately 2.83. Yes? So 45 degrees, positive or negative? You just give me positive or negative. I know it's 2.83. Positive. 135. Positive. 225. Negative. 315. Negative. So my first one is at the point 4, 0. Which would be right there. Bless you. My second one would be at 2.83. 1, 2, 3. 1, 2, 3. So it would be kind of somewhere in there-ish. At 90 degrees, it's 0, 4. At 135, it's negative 2.83, positive 2.83. At 180 degrees, it's negative 4, 0. At 225, it's negative 2.83, negative 2.83. At 270, it's 0, negative 4. At 315, it's 2.83, negative 2.83. And at 360, we're back to 4, 0. What shape did we make? A circle. Yep. So draw a circle as best as you can. not gonna lie to you, that's one of the best circles I ever drew. Telling you that right now. What's up? Because it'd be very hard for us to figure out where 2 squares of 2 is on the actual graph. To apply it to a graph, yes.
Do you want us to run it to 2?
For this one, you don't have to go more than, you don't have to do 3 because, you know what I mean? If we ask for a specific point, then we would want 3. Okay? You know what I mean? Yep. All right? Now, eliminating the parameter in trigonometric ones is a little different because you have to use the hammer. So you have to solve both equations, both functions for t. So if I have x equals 4 cosine of t, excuse me, we're not solving for t. I'm sorry, I misspoke there. We don't solve for t, we solve for the trig. I knew there was a t in it somewhere. So if I have 4 cosine of t, then that's going to be x divided by 4 is cosine of t. If I have y equals 4 sine of t, then that's going to be y divided by 4 equals the sine of t. The hammer says sine or cosine squared plus sine squared is 1. So that would be x, oops, excuse me, I can use colors here. So that would be x over 4 quantity squared plus y over 4 quantity squared is equal to 1. Which would then give me x squared over 16 plus y squared over 16 equals 1. And if I multiply every term by 16, I get x squared plus y squared equals 16, which is the equation of a circle centered at the origin with a radius of 4. Okay? Which is exactly what we had. We had a circle centered at the origin with a radius of 1, 2, 3, 4, all the way around. And if we swing that, if I were to, let's see if I can actually do this. Maybe. No, I don't know if it'll do it. Oh, no, I want those, I want these. There we go. If I swing this around, that's a radius of 4 all the way around. Okay? Good times.